This is the winner of the Exemplary AI track award. It's a paper by Martino, Banchio, and Andrzej Skrzypacz, Artificial Intelligence and Auction Design.
To talk about artificial intelligence and auction design. And the question really comes from the motivation of online advertising auctions, which happen at a rate of, Google says, about 30,000 per second, which is clearly too many for any human or team of humans to play and to adjust bids, right? And so this is why we need algorithms. We need algorithms for the frequency, we need algorithms because it's a very complex world. And the question is, when it's an AI that picks bids, why should we expect the AI to behave like a rational agent? In principle, there's no reason. And all the design that we have, and all the nice theory about auction design and auction theory, really works only for rational agents, as we show in this paper. So in this paper, we try to answer these questions by looking at the simplest possible setting. It's a setting with two agents, and both agents having the same fixed private values, at least for this talk. And we're going to look at the difference between first price and second price auction, the simplest possible auction designs there are. And as algorithms, we're going to choose Q-learning. Q-learning, which is a very simple algorithm again. We're not going to use any deep machine learning here. It's just going to be tabular, because this allows us to give some interpretation to what we find. And the main results of this paper, as a preview, are that bidders' profits are actually much higher in the first price than in the second price auction. And in the second price auction, bidders converge to playing the static Nash equilibrium. So despite similar repeated and static game effects, looks like auction design matters in this world. In particular, we show that with additional feedback, which I'm going to define soon enough, competition is going to be restored in the first price auction as well. So there is scope for mechanism designers to look through and parse the auction for what are the algorithms that are playing and how can we design better mechanisms for them. So the model is a very simple model, as I said. There's two bidders, and each bidder has a value of $1 for winning the auction. The auctions are arranged in an infinite sequence. And in each period, each agent chooses simultaneously from a grid of bids. We like the grid because this allows us to use tabular Q-learning, which is much more interpretable than anything else. And of course, the higher bidder wins, and in case of a tie, winner is determined randomly. Now, the difference between first price and second price, as we all know, is the difference in what is paid by the winner. Well, the winner pays his bid in the first price, whereas in the second price auction, the winner pays the loser's bid. Now, what are the equilibria of these auctions? It's worth going through this calculation, at least because this is not the traditional setting where values are drawn from some distribution, but values are fixed, right? And so in the static game, the first and second price auction have the same identical equilibrium, which is that both bidders bid the same bid, 95 cents each. This is the top of the distribution that we allowed bids to be drawn from. Now, the first price auction has another Nash equilibrium here, which is 90 cents each. And this is just by means of discretizing the space. But as this discretization becomes finer and finer, these two equilibria come close together, and so it really doesn't quite matter as much as one would think. Now, what happens in the repeated game? Of course, we have a plethora of repeated game equilibria. We're going to look at the best equilibrium there is, the Grim trigger strategy, where both bidders bid the minimum bid. They win 50% chance. And then if someone deviates, we go to play static Nash forever. There's a slight difference in the critical discount factor. Reason is that the second price auction has a slightly better deviation. But the discount factor the critical discount factor is very close. It's like 50%, right? So we look at this and we see, it looks like the two games are very similar to each other. So what is the algorithm that we use? I think most people here are sort of familiar with Q-learning, but the idea behind Q-learning is really just to estimate a dynamic programming problem. So Q-learning is an action value function instead of the traditional value function. So for each action, I assign a continuation value. And to estimate this, I use iteration. And so I'm going to use at time t+1, I'm going to say that the estimate of action B is going to be a convex combination with parameter alpha between yesterday's estimate, qt, of the action B, and today's estimate. And today's estimate is simply a sum of today's reward for that action that I observed, plus gamma, discount factor, times max of qt. And max of qt here plays the role of future payoffs, which I'm bootstrapping from today's estimate, because again, I don't have those. And so in this world, we have two hyperparameters. One is alpha, which is a learning rate, and one is gamma, which is a discount factor. Everybody is familiar with discount factors. It's how much I care about the future, right? Alpha here is how much I care about the past, because a high alpha is telling me that I forget about the past very quickly. And a low alpha instead tells me that there's a lot of path dependence in the actions I play. And so in my specification, we're going to have alpha equal to 5%, so a lot of slow learning, I want to say, whereas gamma is going to be really high, 99%. And this really high gamma comes essentially from the fact that these auctions run, again, at a very high frequency, so the future is really just today. And the action selection that we choose is epsilon greedy. This is a simple action selection which trades off exploration and exploitation according to some randomness. So we draw from a uniform distribution, and with probability 1 minus epsilon, we're going to take the exploitative action, where we choose the action that corresponds to the highest value of q. With probability epsilon instead, we're going to randomly draw from one of the other actions. So the main result can be visualized by means of a heat map. And so the heat map here is produced, I'll show you in a second, by simulating these algorithms for 1,000,000 periods and doing this 1,000 times. And so these are the results when these algorithms converge. And remember, I'm taking epsilon down to 0, so I'm trading off exploration exploitation over time. I'm becoming only exploitative, right? And so these algorithms do, in fact, converge. So on the left-hand side, I have a first price, and on the right-hand side, I have a second price auction. On the x-axis, I have the bids of the first player, and on the y-axis, I have the bids of the second player. Now, you cannot see the number, but that's 1,000. So all of the auctions here converge on the top bid, 95 cents each, which means that in the second price auction, we always learn the Nash equilibrium. What's happening in the first price instead, it looks like these algorithms are colluding with each other. They're playing such low bids, 10 cents, 15 cents, right? And they're playing particularly the same bid at the same time. So it looks like it's an equilibrium. It looks like they're splitting the wins with each other. Now, one question that could come up sort of natural here is, maybe because we're killing exploration over time, they just don't realize that there's a better bid, right? Because at the end of the day, if you're exploring, you're bound to realize that you could just increase your bid a little bit and you could do better, right? And so I simulate the same thing for 100 million periods, but without killing exploration. So exploration now is going to be constant at 0.1% forever. Now, the second price auction looks sort of similar, right? Most of the periods are actually spent in the Nash equilibrium. The first price auction looks surprisingly similar. And what this means in particular is that in the first price auction, we're never converging really to any outcome, but we're cycling between different pairs of bids, between 10 and 40 cents, right? So this is not a convergence argument, right? What we observed in the previous figure is just a representation of the distribution. So then the question is, why is tacit collusion happening in the first price but not in the second price auction? As we said, the equilibria looks almost identical, right? And to tell these two formats apart, what we did was run a bunch of experiments in a very experimental paper. And I'm not going to tell you all about the experiments. There's too many, but if you can go look at the paper, I'm just going to talk about a couple that I think give us a good understanding of what the forces are, and then I'm going to give you what we think is the force driving the result. First of all, the first explanation that comes to mind is, okay, maybe second price auction is super easy. Second price auction has a dominant strategy, and we all know that dominant strategy is the easiest thing we can come up with, maybe slightly worse than obviously dominant. So one way to test for this is let's try different auction formats that are in between first and second price, because none of those is going to be dominant strategy, right? We call those alpha price auctions. So instead of paying the first or the second price, I pay a convex combination of the first and second price. These auctions don't have a dominant strategy, And you can tell that even in the 1.6 auction, almost 80% of the time, even more, we actually converge to the static Nash. We collude sort of continuously between first and second price auction. The percentage of simulations that collude looks continuously changing. And so it can't really be dominant strategy. If that was the case, this result wouldn't be particularly consistent. Another guess that comes up pretty quickly is maybe it's just really hard to find a collusive pair in the second price auction. To test for that, we actually initialize the algorithms in a collusive pair. And the first price auction here is denoted by a blue line. And you can see that the blue line sort of spends some time at 40 cents, then moves away, tries something else, right, for a while, and then converges on 20 cents. Really likes these low bids. The first price auction instead spends some time at 40 cents. So, at the end of the day, we told it that it was a pretty good strategy, and then realizes that 95 cents it's better, even though it's worse. And so I find instructive to understand the forces behind this to look at the following graph, which shows the path of bids of those cycles that I talked about in the first price auction. So if we run through the graph from left to right, what's happening here is that the two bidders are playing, let's say, 15 cents each, and then someone deviates. Someone deviates, and a period of intense exploration ensues, right? It's about 50 cents, the median bid. And then they somehow re-coordinate on 20 cents. Now, after 20 cents, another period of intense exploration, and then they re-coordinate on 30. So these cycles look like after bidding the same pair, when some of us deviate, we get punished. We get punished by a period of intense exploration, which is way worse for our payoffs on average. And then we find our way back. And we find our way back in an increasing manner. And then at some point at 45 cents, 40, 35, we realize that, OK, it's time to go back to 15 cents. This looks like a lot like the reward punishment schemes, even though there is no reward or punishment here, because there's no states that it can condition on. So the intuition that we have for what's going on here is the following mechanism. Let's suppose that we're bidding at 20 cents each. And then one of us decides to deviate to 60 cents. Well, the other person definitely has an incentive to catch up to 60 cents, maybe even overbid and bid 65 out of spite, right? But the difference lies in the first price versus second price in what's the winner is doing. Because the winner at 60 cents is happy, but in the first price, he would be happier at 40, even happier at 25, right? I want to overbid by the smallest possible amount. In the second price auction, this incentive is not there. In the second price auction, I'm happy overbidding any amount, because at the end of the day, I'm always paying your price. So this difference in forces creates an asymmetry, because in the second price auction, the only force that comes up is that the losing bidder always wants to go up, but there's no force pushing them down. In the first price, instead, there's always a force pushing down the higher bidder. And so these are the graphs when I introduce an additional force in the mechanism. Of course, it's impossible to replicate the same force in the exploration. But we can see that finally, in the second price auction, we observe some collusion. Of course, there's going to be still a lot of competition, a lot of static Nash that is played. But we finally see some outcomes that are in the lower part of the diagonal. And so we interpret this as a signal that this is indeed the force. The force that is missing in the second price auction is a push towards lower bids. So far I told you that the first price and the second price auction are different, and one of them is more collusive than the other. This is already an auction design suggestion. Maybe use second price auction. But we have a lot of other design choices that tells us that the second price is not as good as the first price. For example, obviously strategy, obviously credibility, right? So maybe we really want to stick to the first price auction. Then is there any way that by tinkering in the auction format, we can restore competition? And the answer comes actually from industry. Because Google Ad Manager, when they switched from second price to first price in 2019, started also delivering the winning bid to all competitors. On the left here, I have the API that Google Manager provides. And you can see that there's a variable, minimum bid to win, which is the minimum bid that is necessary for each bidder to win that auction. This is always communicated to every algorithm. What this does in our context is that it provides enough information to all the bidders to compute their counterfactual evaluations. What would have happened had I bid 60 cents here? What would have happened had I bid 90, right? With this information, first price auction becomes immediately competitive. This is the simulation when the first price auction actually computes counterfactuals and updates every entry of the Q vector at the same time. You can see that they coordinate on one of the two Nash equilibria, the 90 cents one, not the 95. But they coordinate really well, because on the right-hand side here, even when they realize that, yes, bidding 20 cents, both of us is nice, almost immediately they revert back to 90 cents. So in summary, in this talk, I told you that first price auction looks like it's collusive. Looks like there's a problem with first price auction. But I give you two solutions. One of the solutions is that we can move to a second price auction. And this is an easy solution as long as we have the power to do so. But maybe, if we really like first price auction, we can use the second solution, which is that we can provide additional feedback for the first price auction and restore competition there. Now, this later point, the point of providing additional feedback, turns out to be much more general than what we find here. And I have a follow-up paper that actually develops this point in a mechanism design setting. This is all I have. Thank you.
Very great work. Especially it revealed some property in the auction when people are actually interacting with each other. But I have noticed that nowadays, in recent years, many companies in the advertisement auction are actually moving from second price auction to first price auction. Why do you think this will happen if a second price auction will actually get a higher revenue in your model?
That's a great question. I think the answer comes from other papers and not from this one. In particular, Credible Mechanisms says that second price auction is not particularly credible, and the mechanism designer can potentially manipulate the mechanism more than in the first price. The point that we make is more of a point about what happens when you use these specific algorithms. It's not clear that these algorithms are in fact used in practice. And these algorithms are in fact very simple, right? And so probably with more sophisticated algorithm, the effects would be different. But this is sort of a stepping point to analyze more complicated algorithm in a framework similar to what we're doing.
Thanks.
Yeah, very interesting. The first question actually foreshadows my question. So since people moving from second price to first price mostly because of credibility reasons, then the second solution we might relying the feedback provided by the platform will be a problem, right? Because the platform might not credibly provide the true feedback, the winning auction to the advertisers. Do you have anything to say about it?
I think that this, the intuition about the feedback is valid even for different algorithms. So in the follow-up paper, I can show that this is actually true for a wide class of adaptive algorithms. And in particular, there's other papers that do regret minimization, and some of those papers require knowledge of the feedback to update all of the statistics at once.
Yeah, my point is then that it relies on the advertisers to trust the feedback provided by the platform truthful, right? If this assumption is not does not hold, then it will break down.
I agree. Absolutely.
We have two online questions. One from Masha Babayev. How crucial is it that there are just two agents?
We have simulations for 3. It requires increasing the discount factor a little bit to obtain the same collusion result in the first price auction. Collusion sort of shifts up a little bit in the case with 3 agents, but it still looks like the first price auction is collusive and the second price is not.
Okay. I think I'll ask Jason to ask your question yourself.
Yeah, hi, thanks for the talk. I guess I'm interested in your thoughts on the relation between the partial feedback and the full feedback model, and online learning versus multi-arm bandit learning. And there's a reduction that if you are in a partial feedback world, you can actually get learning algorithms to behave as well as if they were in the full feedback world using multi-arm bandit methods, which is the same as getting full feedback. And so I'm a little bit curious as to, should I interpret your results as the agents are using bad learning algorithms, or like what's the interpretation?
I think, thank you. This is a good question. I think the result really works because these agents are bad learning algorithms. And the problem I have, or the suggestion I have here is that it's true that we have this correspondence between partial information and full information, but we can be assured that algorithms are going to be chosen according to these directions. And what we're afraid, I guess, as economists is, what if people are using bad learning algorithms? We still need to say something, and we still want to make our mechanisms robust to this sort of misspecification of the algorithm, for example. And so in that context, I think providing feedback would help, even when the algorithm is sort of less than optimal.
Okay, we have time for one more question from the audience.
Thanks for the nice talk. So I guess I have two questions about the next step. So first, how does this generalize to more than two agents? And second is that, have you considered any intuitions on if I set a reserve value, reserve bit, will that help collusion?
Yeah, so in the paper we have a lot of these robustness checks. One of them has 3 agents. With more than 3 agents, we didn't really go because these are take quite a while to converge. And so it becomes sort of an exercise in adding more and more players. And we think that the point comes across pretty nicely with just 2. With respect to the reserve price, we do try these results as well with this reserve price. And we see that in the second price auction, the result doesn't change. The first price auction result actually does, and the distribution gets truncated, essentially, at the reserve price. And so all the mass shifts to the rest of the distribution upward.